Now that we've factorized this cubic function, we're going to learn how to sketch it. So we have it in factorized form here, which means that we can directly get our x-intercepts from this form by letting this equal 0 and using null factor law to get our x-intercepts. So if we let f of x equal 0, what we end up getting is x is equal to 2, x is equal to 4, or x is equal to negative 3. So these are going to be our 3 x-intercepts. Now, cubic function, it has a degree 3, is a degree 3 polynomial. So that means that we have a maximum amount of x-intercepts of 3. We could also have 2, we could also have 1. We actually can't have none for a cubic, which is quite different to a parabola, because for parabolas, we can have none because our parabola can be like this, and it can just skip the x-axis altogether. Unfortunately, that can't happen for cubics, and that's just because of the nature of a odd degree polynomial. So in this case, it's degree 3, so it has different properties than an even degree polynomial. So these are our 3 x-intercepts here. So we can put them in now. So x is equal to 2, x is equal to 4, x is equal to negative 3, roughly split up like that. Now, if we let x equal 0, we get our y-intercept. So f of 0 is going to be negative 2 multiplied with negative 4 multiplied with positive 3. This becomes positive 24. So our y-intercept will be something like this. Cool. So now what we have to do is pretty much just connect the dots. One thing that we're going to be missing from this graph is actually our turning points. And the reason for that is because we can't actually find our turning points without learning differentiation first. So you might have learned differentiation last year, and you know you can get turning points from differentiation because that's where you have stationary points or gradients of 0 for those specific points. In this case, we can't actually do that. So that's why we're just going to ignore the turning points for now. We're just going to assume where they are roughly based on the shape that we're given, but we don't have to put it into coordinate form. The last thing we need to do, and this is actually the most important thing that a lot of people overlook, it's the fact that we have a positive cubic here, and positive cubic has a general shape of this. So I'm just going to call this the general shape, and I would actually classify this as part of my working out because this allows us to assume that we start off in the negative infinite region, we go up through this intercept, we come back down, we go back up again, and we go towards positive infinity. And that assumption is purely made on the fact that we have a general shape of this, and that's because we have a positive cubic. So we just have to make sure that we specify that so the examiner knows our working out and knows where we're actually coming from. Cool. So let's go ahead and give this a go. Again, this is not going to be the most accurate graph, but it's more so because we're just limited with the resources that we have, purely because we haven't learned differentiation yet. But this should be a roughly good sketch, something along those lines. So we have a y-intercept at 0, 24. We have x-intercept at 2, 0. We have 4, 0. And we also have negative 3, 0 as well. Now we saw in the previous example that we had 3 linear factors factorized together, and when multiplied, they produce a cubic function. So that actually allowed us to have the general shape that looks something like this, where we dipped down from, well, we started off in negative infinite region, we dip up, we dip back down, and we go back up to positive infinite region. So that actually allows us to have 3 x-intercepts in that case, in that specific case, but it could have 2, you could have 1 as well, just depending on the y translation. Now, this cubic here is technically a cubic again, but it looks completely different to this type of cubic. Now, this is, I would say, rarer, but it's still possible, so it's still important to know that cubics can be in this type of form here. And I would call this point of inflection form, and what it kind of looks like is it kind of looks like this. It looks like an x cubed shape, so if y is equal to x cubed, you might have seen the most basic form for a cubic, it looks something like that. This is what this looks like again, but it's just kind of translated through this -1 and this +8 there. And it's kind of analogous to our turning point form, where the negative of this value gives us our x key point, and then this value gives us our y key point. So we're going to use that information to find our middle point, which is there. We call that the point of inflection, and we can use that to sketch our curve. So the point of inflection, how we calculate it, again, is exactly the same as a turning point. It's going to be the negative of this value here, which becomes +1, and then we take the value on the outside, which is +8. And that's going to be the key inflection point on our cubic function. And the function is instantaneously flat. So it's the same as if you have a turning point. A turning point is flat when it turns, obviously, because it has to go from the negative to the positive direction, or vice versa. A point of inflection is also flat as well, but a lot of people forget this because you start off in one direction, you flatten off, but then you keep going in that same direction again. But at this instant here, it is flat, so just keep that in mind whenever you're sketching. We can also get the y-intercept and the x-intercept as well. So we're going to find the y-intercept first. F of 0 is going to be equal 0 minus 1 cubed plus 8. -1 cubed stays as -1. plus 8 is equal to positive 7. And then we could also find our x-intercept by letting y equal 0. So we get 0 is equal to x minus 1 cubed plus 8. Negative 8 is equal to x minus 1 cubed. Now, if we have negative 8 cubed, negative 8 and the cube root of that to move the power of 3 across, we can actually cube root negative values. So you can root negative values if it's an odd power. So in this case, because we have cubed, we can cube root on the other side. We could also do a fifth root to the other side as well if we wanted to. You just can't do even roots because you can't have a negative number multiplied by a negative number to become a negative number again. So, but negative number multiplied by itself 3 times remains negative. So this will just become the cube root of negative 8, which is equal to negative 2, is equal to x minus 1. Therefore, x is going to equal negative 2 plus 1, which becomes minus 1. And this is all the information that we need. So I actually haven't sketched my axes yet, but let's just do a quick one here. Just a quick sketch just to get a representation of what this looks like. Positive 1, positive 8 for our point of inflection is roughly there. Then we have a y-intercept at 0,7, which makes sense. And then we have an x-intercept at negative 2. So our shape is going to look something like this. The scale is kind of bad, but hopefully you get the picture. It looks something like that, where we flattened off at this 1,8. Then we have 7 here, and we have negative 2 there as our final graph. Now, this final form for a cubic equation is very similar to the first form where we have a factorized cubic with 3 separate linear factors. But in this case, we have something called a repeating factor. And it's more common when you have higher degree polynomials because obviously there's more factors to be multiplied together. So in this case, we technically have 3 factors, but it's just that one is repeating. And it actually exhibits different properties when we sketch it on our Cartesian plane. So if we just solve the x-intercepts just algebraically, we just let f of x or our equation equal to 0, and we end up getting x is equal to 1 from that factor, and we end up getting x is equal to negative 2 from that factor. So we see we only have 2 factors, but we don't really know, just by looking at it, how it's represented on a Cartesian plane. So let's go to the Cartesian plane and see how this is represented. Now, what the squared is actually doing is it's creating an intercept, but it also is creating a turning point at the same time. And the turning point is denoted by that squared there. So we know if we have a factor and it's squared, we have a turning point as well as an intercept. They might be thinking, how can we have both of them at the same time? What it's going to look like, I might not sketch it here because I don't want to interrupt this graph here, but just in general, if you have an intercept that's also a turning point, what happens is that your intercept kind of scrapes against the x-axis like that. So maybe I'll just zoom in on that far camera, you can see that we bounce off that x-axis, so it becomes an intercept, but then it goes back in the same direction that it came from. And then it might scoop up again, and this might be a normal intercept here. So you can see in total, in this example, we have 2 intercepts. Our one actually looks very similar to what I've sketched there accidentally. But we see here that we have 1 intercept there, 1 intercept there. So we have 2 x-intercepts in total, but it's still a cubic equation. And the reason for that is because this turning point here, only gives us 1 x-intercept, and then the other one's just a normal x-intercept. So we can kind of classify this as a regular intercept, and we can classify this as a turning point intercept. Now, if you have a cubed, let's say, maybe we'll go through that when we go through high degree polynomials, because again, that's more likely. Let's say if we have a quartic, which is a 4th degree polynomial, or something higher than that. So let's say we had a cubed factor. What's going to happen is that we have an intercept that's actually a point of inflection as well. So you can see the pattern kind of accumulating from our previous knowledge. If something is squared, it's turning point. If something's cubed, it's point of inflection, and that pattern kind of continues. Awesome. Let's find our y-intercept. F of 0 is equal to 0 minus 1 multiplied with 0 plus 2 squared. So this becomes negative 1 multiplied by 4, which is negative 4 for our y-intercept. So negative 4 is going to be somewhere here. And then we have negative 2 as one of our intercepts, but that's going to be the turning point intercept. And then we have positive 1 like that. So if we connect this shape, oh, don't forget, general shape is something like this. I'm just going to label this as part of my working out. General shape is something like that because we have a positive cubic, so it starts in the negative infinite region, goes up to the positive infinite region. So let's sketch this now. So we have the turning point intercept there, just scrapes against the x-axis and bounces back down. And again, we don't know where the other turning point is in this case. I'm just going to assume it's before the y-axis, but it could be anywhere. And again, we don't have the tools and the information to actually help us find this right now. This is going to be 0, negative 4. This is going to be positive 1, 0. This is going to be negative 2, 0. And this is our final shape of f of x. once you've perfected cubics, sketching higher degree polynomials actually becomes very easy. A lot of the skills are just recycled. It's just a matter of considering that when you have a high degree polynomial, you might have a bit more complexity. So I have two very similar examples with just slight differences in them, and we're just going to do them both and show you how these slight differences kind of cause changes in our high degree polynomials when we're sketching them. So we see in the first case that we have f of x is equal to x minus 2 squared multiplied with x plus 3 squared. So this is a quartic because our degrees add up to 2 plus 2, which is 4. So we can kind of anticipate what the shape is kind of going to look like. But if you have an even powered polynomial or even degree polynomial, then you start and finish in the same region. What I mean by that is if we have, let's say, x squared, we know that it looks like this. X cubed looks like this in its most basic form. X to the power 4 is kind of similar to x squared in the sense that it might be like more complicated in the middle or something like that in most cases, but it still starts and finishes in the same region if it's positive. So if it's a positive quartic, then it starts and finishes in the positive region. If it's a negative, then it starts and finishes in the negative region. But then for odd powered polynomials, it's different. You alternate the positive and the negative region for the start and the finish respectively. So we just have to consider that when sketching these polynomials here. So again, it's a degree 4 and it's positive, so we know the general shape and roughly what it's going to look like. So we have x-intercepts at positive 2 there, and then we have negative 3 over there. So I'm just going to sketch them in. I might use a different color actually. So we have negative 3 here, positive 2 here, and they're both turning points on the x-intercepts because they're both powered by 2. So they're still x-intercepts, but because they're raised to a power of 2, they're repeating factors and they're turning points because it's squared. So this is going to be a turning point on the x-axis. This is going to be a turning point on the x-axis, and it's a positively shaped quartic, which means it has to look something like this. So it's going to come from the positive region, scrape against the x-axis like that, come back up to turn again, and then it's going to, oh my goodness, it's going to scrape against the x-axis like that again. Okay, imagine that lied on the same point. You can kind of get the picture, but actually let's rub this out because it's actually quite annoying. It's going to look something more like this. Yeah, perfect. Let's just fill in the x and y axes there. Awesome. So this is what the graph would roughly look like. I'm not going to put in any values or anything like that. I just want to show you how the general process is, and then you could go ahead and find all the points that you can. So it would be the y-intercept, and that's actually pretty much it because you can't find that turning point there without differentiation. But this is how you get the shape of this graph here. Maybe I'll just label these just for your clarification. So we have negative 3 from that factor, and we have 2 from that factor there. So that's what the shape is going to look like. So that's kind of the thought process that we would go through. Now this one's slightly different, so I'm going to show you how the thought process slightly changes. We have f of x is equal to negative of x minus 2 squared outside of x plus 3 cubed. So you can see there's two main differences. The first one is the negative on the outside, so how does that change the graph? And the next one is instead of a squared from the first one, we have a cubed here now. So how does the cubed change our shape? And how does it change the degree of the polynomial? So we see now that the degree is a 5. It is the 5th degree polynomial, which means that we start in one location and we finish in the opposite location. And because it's a negative polynomial, we start in the positive region to the left, top corner, and then we go to the negative region as we go down. So we just have to consider that. So the shape might be something along the lines of that, where we start in the positive region here, and then we finish in the negative region there. So again, we have negative 3 and positive 2 as our x-intercepts. And this one is still a turning point intercept, so it's going to scrape against the x-axis, wherever shape it might be. But this one is actually going to be a point of inflection, which is a turning point, which is a x-intercept as well. So let's imagine what that's going to look like. If we're starting from the positive region here, and then we're going downwards, then if this is an x-intercept, then the shape has to be something like this. So it's going to look something like that, because we're starting from the positive region, because we know that from our degree and the sign of our polynomial. Now, the only other x-intercept is at x equals 2, which means that this graph is going to dip back up towards that x-intercept, and then it's going to scrape it and then go back down to the negative region. It's kind of the only possibility that we have in this case. So this is going to be negative 3, this is going to be positive 2, and that's how we determine shapes for higher degree polynomials.